And if you're working from a strong base of data, where then do your opponents find the biggest issues in the work that you're doing?
They would say that there are many lines of evidence. It's not just the supernovae. In fact, most of my colleagues would say that, oh, we always thought there was something dodgy about the supernovae. What about the cosmic microwave background? That's precision cosmology. What about other things, baryon acoustic oscillations and so on? The truth is that all those arguments, as I said, depend on assuming the answer. They are inferences in the framework of the standard cosmological model. If you broaden out the standard cosmological model, then those inferences cannot be drawn, right? And therefore, I think these people really ought to expand their horizons a bit. The reason why they have not done that so far is because they have been told that everything fits so beautifully. Why do you want to try if things fit so beautifully? That actually is a selection effect. There is a strong evidence for what we call selection bias. So, out of, 43 measurements of this cosmological constant since the time it was discovered, you would expect to find a distribution, right? But somebody who studied this pointed out that they are all clustered around the most precise measurement, which was done in the past by something called the WMAP satellite. They're all within one standard deviation of the WMAP satellite. That suggests that there has been an unconscious bias in determining the answer. It is not scattered. So I'm very hopeful that the next generation of experiments will be done with so-called blind hypothesis testing, okay, and that would certainly be progress. That's what we do, for example, at this ice cube experiment. We open the box with the data only after we have formulated the hypothesis that we are going to test.
And what would the ramifications be if you were able to prove that the universe was expanding at an accelerating rate?
Well, that just means that we have to rethink how to construct a cosmology. And I don't think I'm saying anything radical here. I mean, our current model of cosmology goes back 100 years. There is no other domain of human activity I'm aware of, intellectual activity, where we are actually using a 100-year-old model to interpret data today. We certainly don't do that in particle physics. Our standard model of particle physics goes back to the 70s. Well, okay, so that's already 45, 50 years old, but it's not 100 years old, right? And if you think of other fields, I don't know, neuroscience, biology, they're not using 100-year-old theories. We are in cosmology. And the reason why I think we have to move away from that is simply so that we can be courageous enough to accept the universe as it is and not to try to impose this idealized notions of symmetry and perfection upon it, which is really what was done. And it was done because we had no data then. If you don't know something about the universe, anything about the universe, you obviously assume it to be as simple as is possible. But today we have the data. So I think we really have to start again and start constructing a model of cosmology. And hopefully there will be the mathematical breakthroughs that allow us to apply the general theory of relativity to situations which are not as symmetric as the original model. So this is not going to be easy. It's not going to be easy to take into account what I said, that you might see different things in different directions, okay, and that your particular location in the universe might matter. It just complicates things, and people say, why complicate things? Why not stick with the simple model, everyone's happy? Well, I'm not happy because it brings up this dark energy which makes absolutely no sense in physics, in fundamental physics. Astronomers don't understand this. For them it's one number. For us it is the bone in our throat. So I would like to get rid of dark energy, not because it gets rid of the fundamental problem, it just brings back the cosmological constant problem, but it would allow us to re-engage with that problem, which I think possibly will require a real advance in quantum gravity. So currently we have no theory of quantum gravity which can engage with this problem. Neither string theory nor loop quantum gravity have had anything to say about the problem of how vacuum energy couples to gravity. So we'll be forced to confront it, and that I think might lead to progress.
Are there any grand theories, such as like string theory or talk about supersymmetry, but that capture your imagination?
Well, string theory certainly captured all our imaginations when it was formulated. I remember listening in CERN theory lecture room to when the first anomaly cancellation was discovered in string theory. This was 1984, and everyone was thinking, within 2-3 years, everything will be sorted out. Well, that was, what was it, over 36 years ago. That's because it has turned out to be much more difficult than people thought. And the idea was that the strings themselves, their dynamics create the space-time in which the strings move. But that has proved too ambitious a construction. So currently all of string theory is formulated in a flat space-time background, in Minkowski space-time, which means that the real dynamics of what string theory could tell you, we still don't know about. It's just too difficult. It's already very, very difficult at this stage. And the full string theory, nobody really even knows what string theory is. That's what, I know some real string theories, and that's what they tell me, that it's hard to even formulate what is string theory. So in a sense, I guess we are lucky that we have hit upon something like that, which has got such depth and complexity. But at the same time, progress is frustratingly slow. But then that's really because we are impatient. If you look at the history of science, most things took, century to work out. And why do you expect that in 35 years we'll have the answers? So I think we should give string theory more time and string theorists more time. But they should perhaps also be a bit modest and not claim that they're going to solve everything in 3 years.
And what are some future research projects or projects you're involved with at the moment? Where are your work taking you?
Well, I'm, as I said, a phenomenologist. I'm interested in phenomena rather than in high theory, as it were. I'm saving that for when I retire. It's a joke that you start thinking about the nature of time and the measurement problem in quantum mechanics, when you have the leisure in your armchair, because they are difficult problems. And, Kurt Gödel, that's what he said when he finally went to the institute in Princeton. I remember someone interviewed him and he said, "What are you thinking about?" And he said, "The nature of time." And so of course he never made any other contribution to it. It was too hard. So I think I'll reserve those things for later. But right now, apart from phenomenology, of course I'm interested, as many people are, in information. That's the sort of key to, I think, understanding, lots of emergent phenomena like biology. What makes a life form different from the inanimate molecules that you put together to make life. There is clearly additional information in the life form. How that information got embedded, how it gets passed on, that of course is most of biology today, how that information is propagated, and propagated in such an elegant way, and at the same time extremely inefficient way. Most of the information in the DNA is not actually used for synthesizing proteins. We don't know what it is for. And there is clearly a huge amount of evolutionary history written, in the construction of these molecules and how they work together. That's all fascinating stuff. But, we like to keep things simple in physics. We don't like complicated stuff. So the questions we would ask are things like, if I throw a living being into a black hole and then they get evaporated and the black hole radiation contains the information about this person that was thrown in, can we put it together and create that person again? So currently the answer must be, in principle, can we do that? I mean, that's actually become a cutting edge question called the black hole information paradox, as to whether, forget about life, even for an inanimate object, is that possible? And it's not so much that the answer to that question itself is the be all and end of everything, but the act of thinking about it, the kind of tools that you have to develop to think about it, that creates new ways of looking at things. So, as with most intellectual endeavors, I think the journey has to be the reward. We don't really expect to have an unified theory or solve everything, but we should have lots of fun doing it.
And finally, we're at an Arts and Ideas Festival. I wonder why, or if you think big ideas still matter, this sort of endeavour, intellectual endeavour. Why? What drives you? Why? What are you looking for? Or why should it be an important part of our society?
Well, it's like they say, you climb Mount Everest because it's there. So the very fact that we are impelled to think about things that are not directly, let's say, relevant to our survival, that's, I suppose, what makes us sentient beings. I'm not going to say things like, well, it's thinking about these things that make us wonder how to do experiments to test them, and then we build a laboratory called CERN, and then we have a bunch of people in something called the TC building who are there to help the physicists talk to each other. And you know what? One of them invents something called the World Wide Web, and that changes everybody's life forever, right? That's exactly what happened. Tim Berners-Lee was an undergraduate in physics at Oxford, at Queen's, and he worked in the TC building, and he used to work with people who need to communicate independent of, whatever. And that was not foreseen, that was not planned, and that's why it didn't come out of Microsoft, it didn't come out of IBM, it came out of a place where people are just trying to solve problems for the sake of solving problems, right? So I think the material benefits to humankind of what we do should be bleeding obvious. I don't need to spell that out, right? I don't need to give you a list of all the things that has led to. But I don't think that that's the main reason. The main reason we should be doing it is because we are creatures who feel the need to do it, just as we feel the need to draw paintings on cave walls, and we feel the need to dance, we feel the need to make music. So intellectual thought is part of the same, glorious sort of set of abilities that we have. So we should use them in the same way. The only issue is that it costs money, that is true, that is why it has become a political issue. But actually, I don't even need to say this either, it costs very little money. Whole of CERN basically costs as much as one medium-sized university. So there are, I don't know how many hundreds of universities in Europe alone. So you're asking whether you should have one more or one less university. Is that really such a big question? So surely we can afford this.
Great. Thank you so much for taking the time.
Thank you.